Look at the sheer scale of modern offshore wind farms. We construct these multi-million-dollar titans in the middle of the ocean to harvest kinetic energy from some of the harshest environments on Earth. But when maintenance is required, or a storm becomes too severe, operators sitting in control rooms miles away have to remotely disconnect these turbines from the grid. Under normal conditions, electricity flows through this massive infrastructure in a perfectly predictable linear state. It moves in orderly, three-phase sine waves, pulsing rhythmically toward the shore. When an operator hits the switch to cut that connection, the expectation is that the flow stops and the energy state drops to zero. These machines are engineered to withstand the kinetic fury of a winter gale, yet their most vulnerable moment occurs during a controlled shutdown. The mechanical gatekeeper controlling the flow of electricity from the turbine to the grid is called a vacuum circuit breaker. To safely cut the power, this breaker is designed to snap open all three of its electrical phases simultaneously, creating a physical gap that current cannot cross. But occasionally, a microscopic mechanical failure occurs. The switch fires, two poles snap open, but the third pole jams, physically stuck in the closed position. Because of that single remaining point of contact, the turbine is now stranded in an electrical limbo. It is no longer fully connected to the grid, but it is not completely isolated either. That tiny mechanical glitch pushes the entire electrical system out of equilibrium. It silently arms an invisible trap, hidden inside the grid itself. This animated diagram shows a cross-section of a long submarine export cable. Because of how they are constructed, these long cables inadvertently act as a massive capacitor, meaning they excel at storing a vast amount of electrical charge along their length. Wired directly to that cable is the wind turbine's transformer, an inductor with a nonlinear magnetic core. Instead of holding raw electrical charge, it stores energy in a fluctuating magnetic field. When that circuit breaker jams, it forces this capacitor and inductor into a closed circuit. Unable to escape to the grid, the trapped electrical charge and magnetic energy violently pass back and forth between the cable and the transformer. This creates a self-sustaining resonant loop. The energy bounces rapidly, compounding in intensity with every single cycle. The necessary physical architecture of an offshore wind farm, miles of cable wired to heavy transformers, inherently provides perfect ingredients to build this self-sustaining energy snare. This interaction is driven by a transformer with a nonlinear core. As the energy loop intensifies, it pushes that core past its magnetic limit, a state called saturation. At this point, the physics of the system change instantly. The clean, repeating cycles of energy shatter, warping into a rare and erratic phenomenon known as chaotic ferroresonance. In this state, the electrical system is operating entirely unpredictably. It begins bouncing through erratic voltage spikes, unable to bleed off the trapped energy. Translating that math to real-world stakes, the voltage rockets to 3.88 per unit. That is nearly 4 times its normal, safe operational limit. This mathematical anomaly takes a heavy physical toll on the hardware. Inside the transformer, the magnetic core violently saturates, hitting its absolute magnetic limit, and then rapidly desaturates over and over again. This high-speed oscillation generates intense heat and extreme mechanical stress. The critical insulation protecting the inside of the transformer begins breaking down almost immediately. Because this is an undamped loop, the chaos does not fade. It acts as a continuous, relentless hammering on the physical grid, making it far more structural damage than a single massive lightning strike. You cannot stop a chaotic energy loop with brute force. To save the hardware, the trapped energy must be strategically bled off. The most effective solution is a precisely calibrated damping resistor, wired directly into the circuit to intercept the resonant loop. When engaged, the resistor absorbs the erratic thermal energy, neutralizing the chaotic state. The scattered points collapse inward to a stable orbit. The dangerous 3.88 voltage spikes drop to a harmless 1.24 per unit, returning the system to a safe, fundamental harmonic mode. As the global transition toward renewable energy accelerates, we are building highly complex grids that rely on thousands of miles of submarine cables. Building the infrastructure of a renewable future is only half the challenge. The other half is mastering the nonlinear mathematics required to keep that infrastructure stable.